Test-driven transformation. Build better software faster and with confidence. Chapter 1. The hidden costs of crafting code, why TDD matters. Imagine you're building a complex machine, a sophisticated robot arm, perhaps, designed to perform delicate assembly tasks. You spend weeks, maybe months, designing each gear, each circuit, each line of code. Finally, after immense effort, you flick the switch. The arm whirs to life, moves a few inches, then suddenly locks up, emitting a high-pitched whine. A tiny, overlooked screw in one joint has jammed the entire mechanism. Frustration bubbles up. Now, you have to dismantle parts of it to find that one errant component, fix it, reassemble everything, and hope nothing else breaks. This scenario isn't just a physical engineering nightmare. It's a common reality in the world of software development. Developers, teams, and entire organizations often find themselves caught in a cycle of building, discovering bugs, fixing them, and sometimes introducing new ones in the process. The hidden costs of crafting code without a robust, disciplined approach can be staggering, leading to project delays, demoralized teams, and software that's unstable or incredibly difficult to change. The status quo. Common frustrations in software development. Walk into almost any software development office, virtual or physical, and you'll hear variations of the same laments. We're constantly fighting fires. This means a disproportionate amount of time is spent fixing urgent bugs rather than developing new features or innovations. It's like being stuck in firefighting mode all the time, never truly building. It takes forever to make a simple change. Even a seemingly minor tweak sends ripples through the system, often breaking unrelated parts. The code feels like a delicate house of cards where touching one piece threatens collapse. This phenomenon is often rooted in what developers call spaghetti code, tangled, interdependent logic that makes isolated changes nearly impossible. We don't trust our own code. Developers become hesitant to refactor, restructure, and improve existing code, even when they know it could be cleaner or more efficient. The fear of accidentally introducing a critical bug is so high that they'd rather live with suboptimal code. This lack of confidence slows down innovation and builds technical debt. Our release cycles are excruciating. The period leading up to a new software release becomes a tense, high-pressure exercise in manual testing, bug fixes, and desperate attempts to stabilize the product. The process is exhausting and unpredictable. These aren't just minor inconveniences. They are symptoms of deeper issues in how software is conceived, designed, and built. The debt collector. Understanding technical debt. One of the most insidious hidden costs in software development is something known as technical debt. Just like financial debt, technical debt accumulates when quick and dirty solutions are chosen over well-engineered ones. Perhaps you rushed a feature to meet a deadline, knowing it wasn't built optimally. Or maybe a component was designed poorly from the start. Each time this happens, you borrow from the future. Initially, these shortcuts might seem efficient. You deliver something quickly. But then, interest starts to accrue. That interest comes in the form of increased effort for future changes. It becomes harder and slower to add new features or modify existing ones because you're constantly working around the poor initial design. Higher likelihood of bugs. Fragile code is more prone to breaking when touched, leading to more defects. Difficulty in understanding the code. Hacked-together solutions are often convoluted and poorly documented, making it a nightmare for new team members, or even the original author years later, to understand what's going on. Technical debt isn't just about bad code. It's about the consequences of that code on productivity, quality, and morale. And like financial debt, it can cripple a project or even an entire company if left unaddressed. It makes the once agile development process feel like wading through treacle. The bug hunt, why traditional testing often falls short. We test our software, you might say, and that's often true. Many teams employ dedicated quality assurance, QA, testers who manually run through scenarios, trying to break the software. Developers might even write unit tests after they've written their code as a sort of belated validation. While these practices are better than no testing at all, they have significant limitations. Manual testing is slow and expensive. It requires human hours, is prone to human error, and can't be easily repeated with every small code change. As software grows, the time needed for comprehensive manual testing explodes. Testing after the fact is reactive. Finding a bug late in the development cycle, or worse, in production, is far more costly to fix. The longer a bug lives, the more ingrained it becomes, and the more dependent other parts of the system might become on its erroneous behavior. Imagine finding a fundamental flaw in your robot arm after it's been shipped to a customer. Tests written after code often just confirm what you think the code does. If you didn't consider certain edge cases or error conditions while writing the code, you're unlikely to write tests for them afterwards. There's a cognitive bias at play. You're looking for evidence your code works, not actively trying to find its flaws. This traditional approach often results in a perpetual bug hunt, a desperate search for errors that have already been embedded into the system, leading to rushed fixes and a lingering sense of unease about the software's stability. Introducing a transformation, test-driven development. What if there was a way to flip this script? What if, instead of being reactive, you could be proactive? What if every line of code you wrote contributed to a robust, clean, and trustworthy system from the very beginning? Enter test-driven development, TDD. It's not just a testing technique, it's a fundamental shift in how you approach software design and construction. At its heart, TDD is a discipline where you write small, automated tests before you write the actual code that fulfills the requirements. These tests guide your development process, acting as tiny, precise specifications for the behavior you intend to build. Think of it like this. Before adding a new feature to your robot arm, you first write down exactly how that feature should behave in a quantifiable way. You define what inputs it should receive and what outputs it should produce. Only once you have this clear specification, the test, do you then craft the arm's components and programming to meet that exact specification. If a component doesn't meet the spec, the test immediately tells you. This iterative, test-first approach transforms the development process by making you think before you code. You define the desired behavior first, forcing clarity on what you're building. Driving cleaner designs, code that is built to be easily tested tends to be modular, simple, and well-organized, providing immediate feedback. You know instantly if your new code works, and crucially, if it breaks anything existing. Building a safety net. Your suite of automated tests grows with your software, serving as a comprehensive regression suite that ensures past functionality remains intact. Setting expectations, what TDD can and cannot do for you. It's important to approach TDD with realistic expectations. It is not a magic bullet that will eliminate all bugs. No development practice can guarantee 100% bug-free software, but TDD drastically reduces the number of functional defects, especially at the unit level. Make you instantly faster. There is an initial learning curve and a perception that writing tests first slows you down. However, the long-term gains in quality, reduced debugging time, and increased confidence almost always outweigh this initial investment. Solve all your project management problems. TDD addresses a significant part of the technical challenges in software development, but it won't fix poor communication, unclear requirements, or unrealistic deadlines on its own. What TDD will do is empower you to build software in a fundamentally different, more confident, and ultimately more efficient way. It shifts you from a reactive bug-fixing mindset to a proactive design and build approach. It helps you tame the hidden costs of code, transforming your development process, and, by extension, the quality and maintainability of your software. In the chapters that follow, we'll peel back the layers of test-driven development, explore its core mechanics, dive into the profound benefits it offers, and address the common questions and challenges that arise when embracing this transformative approach to software creation. Get ready to rethink how you build. Chapter 2, Understanding the TDD Mindset. Test first, design always. In the previous chapter, we explored the frustrations and hidden costs associated with traditional software development. We saw how technical debt can accumulate, how manual testing falls short, and why a reactive approach to bugs can stifle innovation. Now, it's time to introduce the foundational concept that underpins test-driven development and sets it apart. The radical notion of test first, beyond test after, the fundamental shift. To truly grasp TDD, we must first confront a common, ingrained habit: writing code, then writing tests for that code. This code-first, test-after approach often feels natural, almost intuitive. You think, I need to build this feature, so you dive into writing the functional code. Only once the feature is done, or seems to be, do you consider writing tests to verify its correctness. Sometimes, you might skip testing the new feature altogether, relying on manual checks or hoping for the best. This traditional workflow is fraught with peril. When you write tests after the fact, you often find yourself in a defensive posture. You've already invested time and effort into the code, and now you're simply trying to prove that it works. This can lead to confirmation bias. You might only write tests that confirm your assumptions about how the code should behave, overlooking edge cases or potential failure modes. Difficulty in testing. If the code wasn't designed with testability in mind, it can become incredibly complex to write effective tests for it. Dependencies might be tightly coupled, functions might be enormous, and isolating specific behaviors becomes a monumental task. As a result, tests are often skipped or written poorly, providing little value. Bugs discovered late. Any bugs found during this test-after phase are already embedded in the completed feature, making them more costly and time-consuming to fix. TDD flips this traditional approach on its head. It mandates a fundamental shift. You write the test before you write the code. This isn't just a minor procedural change. It's a profound intellectual and behavioral transformation. It forces you to think about the desired outcome and behavior first, before you even consider the implementation details. The TDD philosophy: using tests to drive design, not just validate it. The core philosophy of TDD can be summed up in a simple phrase: test first, design always. This isn't about writing more tests. It's about using tests as the primary mechanism to drive the design and evolution of your software. Each test acts as a tiny, executable specification for a single piece of behavior you want your software to exhibit. Imagine you're building a simple component, say, a calculator that can add two numbers. In TDD, you wouldn't start by writing the addition logic. Instead, you'd start by writing a test that says, when I add 2 and 3, the result should be 5. This test, at first, would fail because the addition logic doesn't exist yet. This failure is not a setback, it's a deliberate guiding signal. Developing with TDD feels like building something with very precise, immediate feedback. You articulate a tiny requirement, see it fail, satisfy it with minimal effort, and then tidy up. It's a very deliberate, mindful process that contrasts sharply with the often chaotic code-then-fix cycle. Feedback loops: the critical role of rapid feedback. In software development, delayed feedback is an enemy. The longer it takes to discover a mistake or a misunderstanding, the more expensive it becomes to correct. If you only discover a critical bug after a feature has been released to thousands of users, the reputational and financial costs can be immense. TDD thrives on rapid, continuous feedback. By writing a test that fails immediately, you get instant validation that your understanding of the requirement is correct, and that the code you're about to write needs to address that specific behavior. Once you write just enough code to make that test pass, you again get instant feedback confirming your solution is correct and complete for that specific requirement. This tight feedback loop is not just about catching bugs. It's about guiding your development decisions. It's like having a very opinionated, always available colleague looking over your shoulder, constantly telling you, yes, that's what we wanted, or no, that's not quite right yet. This constant validation builds immense confidence and allows you to catch conceptual errors, logic flaws, or misunderstandings of requirements almost immediately. Building with blueprints, analogy of TDD. Think of TDD as akin to constructing a complex building. But instead of a single, sprawling blueprint, you're working with a collection of hundreds or thousands of very small, precise mini blueprints. Each mini blueprint you test specifies a tiny, discrete quality of the building. This window must be exactly this wide, or this support beam must withstand precisely this much load. You don't build the entire wall and then check if the window fits. Instead, you write the specification for the window first, then build just the window to fit that specification. Then you write a specification for the next small piece and build that. When the building is done, you don't need a massive, all-encompassing inspection. You already have a rich collection of all these small, precise blueprints, each of which was checked and verified during construction. If you ever need to change a window, you can refer to its specific blueprint, make the change, and quickly verify that it still meets its requirements and hasn't compromised any adjacent components. This ensures integrity and reduces fear of change. Kent Beck's vision, the genesis of TDD. The concept of test-driven development isn't new. It was rediscovered, or perhaps popularized, by Kent Beck in the late 1990s, while he was developing an accounting framework in Smalltalk. He found that by writing tests before the code, he gained clarity, reduced debugging time, and produced better designs. Beck formalized TDD as a core practice within extreme programming, XP, an agile software development methodology. XP emphasized practices like pair programming, continuous integration, and simple design, all of which TDD complements beautifully. Beck's initial motivation wasn't primarily to create a testing technique, but to solve a deeper problem: how to design software better. He realized that the act of writing the test first forced him to consider the API, application programming interface, or the external interface of his code, leading to more flexible and usable designs. The tests were not an afterthought but a design tool, guiding him towards smaller, more focused, and more easily composable pieces of code. So, when you embrace TDD, you're not just adopting a new way to test. You're adopting a new way to think about software development, a disciplined, iterative, and design-centric approach that promises to transform the way you build software and, ultimately, the quality of the software you deliver. Chapter 3. The Red-Green-Refactor cycle, your new development rhythm. If TDD has a heart, it beats in a rhythm of 3 distinct phases: red, green, and refactor. This cycle is the practical, iterative engine that drives development in a test-driven manner. Understanding this rhythm is crucial, as it's the choreography of every piece of code you'll build with TDD. It's akin to a dance. Each step is deliberate, serving a clear purpose, and building upon the last. Let's break down each phase of this indispensable cycle. The heartbeat of TDD, Red-Green-Refactor. Imagine a traffic light system that guides your coding. You start at red, move to green, and then, only after everything is stable, you step back to refactor. And then you repeat for every tiny piece of functionality you add. Red, write a failing test. The cycle always begins here. This is the test-first mantra in action. Your first step is to write a small, focused, automated test that describes a single, specific piece of functionality or behavior that does not yet exist. Why red? When you run this newly written test, it must fail. This failure is a crucial signal. It tells you 2 things: the feature doesn't exist yet, a logical outcome since you haven't written the actual code. Your test is valid. The test is correctly identified as failing, meaning it would pass if the code were implemented. If your test passed immediately, it might be testing nothing, or testing something that already works, which isn't guiding new development. The simplest possible test. This is a key principle. Don't try to test an entire feature all at once. Focus on the absolute smallest, most trivial piece of behavior that defines some aspect of what you want to build. Analogy. If you're building a car, you don't start by writing a test for the car drives at 60 mph. You might start with the accelerator pedal can be pressed. Even simpler, if you're building a calculator's addition function, your first test isn't for complex sums. It might be, given 2 numbers 1 and 1, the add function should return 2. What you are doing, you are defining a requirement in an executable way. You are telling your software, hey, when I give you this input, I expect this output. The resulting failure is a clear, unambiguous signal that this expectation isn't met yet. Green, write just enough code to make the test pass. This is where you write the functional code, but with a strict limitation. Only write the minimum amount of code necessary to make the previously failing test pass. Why green? Once you've written this minimal code and run your tests again, your new test and all previous tests should now pass. Your traffic light turns green, signifying that the current defined behavior is working. The just enough principle. This is incredibly important. Do not over-engineer. Do not try to anticipate future requirements. Do not add extra logic that isn't directly necessary to satisfy the current failing test. If the test says, 1 plus 1 should be 2, your code might initially be a simple return 2. If the next test says 1 plus 2 should be 3, your code might evolve to return operand 1 plus operand 2. The code evolves incrementally, driven by the tests. Analogy. Sticking with the car, if your test was the accelerator pedal can be pressed, you don't build the entire engine and transmission. You build just enough to make the pedal depress, perhaps a simple spring mechanism. What you are doing. You are moving from a defined requirement, red test, to a fulfilled requirement, green test. The goal here is solely to achieve passing tests, even if the code written is not elegant or fully generalized yet. We'll handle that in the next step. Refactor, improve the code. Once you have a green light, all your tests are passing, you have earned the right to refactor. This phase is about improving the design, structure, and readability of your code without changing its external behavior. Critically, while refactoring, all your tests must continue to pass. Why refactor? The code you wrote in the green phase was focused on just passing the test. It might be simplistic, perhaps even a bit ugly or inefficient. Now that you have a comprehensive suite of passing tests acting as a safety net, you can confidently clean up your code. Analogy. You've built a primitive accelerator pedal that can be pressed. Now, with the knowledge that it works, you can refine its mechanics, use better materials, make it more ergonomic, perhaps connect it to more sophisticated systems, all while ensuring it still performs its core function of being pressed. What you are doing? You are addressing technical debt proactively. This might involve renaming variables or functions for clarity, extracting duplicate code into reusable functions, simplifying complex logic, improving the code's efficiency or readability, applying design patterns to improve structure. Crucially, if any test fails during refactoring, it's an immediate signal that you've changed the behavior of the code, which is exactly what a good test suite should prevent. You then revert the change or fix the refactoring until all tests pass again. The safety net. The suite of passing tests built up during the red and green phases acts as an unbreakable safety net. You can confidently make changes, knowing that if you inadvertently break existing functionality, a test will immediately alert you. This dramatically reduces the fear of changing code and encourages continuous improvement. The small steps principle. Why small, incremental changes are key. The power of the Red-Green-Refactor cycle lies in the smallness of each step. You're not tackling huge features. You're chipping away at them, one tiny, verifiable behavior at a time. You write one small test. You write the minimal code to pass that one test. You refactor that small piece of code. Then, and only then, do you repeat the cycle for the next small test. This meticulous approach might seem slower at first glance, but it provides continuous momentum and clarity. You're never far from a working, stable codebase. You're always receiving feedback. You limit the scope of potential errors and, therefore, the time spent debugging. It prevents you from getting lost in the complexity of a large problem. Instead, you break it down into manageable, solvable tasks. The confidence cycle, how each cycle builds assurance. As you move through these mini cycles, something profound happens. You build confidence. Every time you write a failing test, make it pass, and then refactor successfully, you reinforce your understanding of the problem and your ability to solve it. Moreover, your growing suite of tests becomes a robust form of executable documentation and, more importantly, a regression safety net. You can later make significant changes to your code, knowing that if you inadvertently introduce a bug or degrade existing functionality, your tests will immediately catch it. This confidence liberates you to refactor aggressively, to explore alternative designs, and to keep your code base clean and adaptable. It changes coding from a high-wire act to a well-supported engineering process. Mastering the Red-Green-Refactor cycle is not about rigidly following a prescription. It's about internalizing a rhythm, building a habit, and developing a discipline that transforms the very act of writing software. It's about being deliberate, receiving constant feedback, and continuously improving your craft. This iterative dance, repeated over and over, is the secret heartbeat of the test-driven transformation. Chapter 4. The Silent Architects, How Tests Drive Superior Design. When TDD is discussed, the initial focus often lands on quality control. It helps catch bugs, or it ensures correctness. While undeniably true, these benefits only scratch the surface. The most profound, yet often overlooked, advantage of test-driven development is its powerful influence on software design. TDD acts as a silent architect, subtly guiding you towards cleaner, more modular, and inherently more maintainable code, almost as a side effect of its process. Testability as a design metric. Consider this: when you write a test first, you need to be able to interact with the piece of code you intend to test. You need to provide it with inputs and observe its outputs, all in an isolated, predictable manner. This immediate necessity forces a powerful design constraint: testability. If a piece of code is hard to test, it's often a clear indicator that its design is flawed. It might be too tightly coupled. Its functionality is deeply intertwined with many other parts of the system, making it impossible to test in isolation. Having too many responsibilities. It's trying to do too many things, thus making its individual behaviors difficult to pin down and verify. Dependent on external factors. It relies directly on databases, network calls, or user interfaces without clear ways to substitute or control those dependencies during a test. When you start with a test, you realize these design flaws before you even write the problematic code. Your test will simply be too difficult or awkward to write. This immediate feedback compels you to design the code in a way that makes it testable. And code that is testable is, by its very nature, often better designed. It tends to be modular, broken into smaller, self-contained units. Loosely coupled, dependencies are managed and injected rather than hard-coded, allowing components to be swapped out for testing. Single responsibility. Each unit does one thing and does it well. This feedback loop means TDD doesn't just verify your code, it helps shape it. The test becomes a design tool, pushing you towards elegant, separated concerns. Modularity and decoupling. The natural outcome. Imagine building a complex Lego castle. If each and every brick was permanently glued to its neighbors, changing even a small section would require dismantling and rebuilding much of the castle. This is what tightly coupled code feels like. TDD naturally encourages modularity and decoupling. Modularity. Because you typically test small, isolated units of behavior, you're compelled to think about your code in terms of these smaller, independent modules. Each module has a clear purpose and a well-defined boundary. This makes the overall system easier to understand, reason about, and manage. It's like designing your Lego castle with distinct, independent towers, walls, and drawbridges that fit together but can also be worked on separately. Decoupling. When a test focuses on a single unit, that unit needs to be independent of its external collaborators, like a database, a network service, or another complex part of the system. To achieve this in a test, developers often use conceptual test doubles, like mock objects or stubs, which we'll touch upon briefly in a later chapter. The act of setting up these test doubles forces you to design your code so that these dependencies can be plugged in, rather than hard-coded. This makes your code inherently more flexible and reusable, reducing the gluing between components. The result is a highly adaptable system where changes in one area are less likely to ripple destructively through others. This is a hallmark of good software design, and TDD helps you arrive there organically. Clarity and simplicity. When tests are explanations. When you write tests first, focusing on one small behavior at a time, each test becomes a mini specification for that behavior. This naturally leads to simpler, more focused code modules. If a piece of code is trying to do too much, writing a clear, concise test for it becomes difficult. This difficulty is a red flag, prompting you to break down the complex logic into smaller, more manageable units, each verifiable by its own simple test. More often than not, simpler code is easier to understand, its purpose is immediately apparent. Easier to debug, issues are isolated to small sections. More reliable, fewer moving parts mean fewer opportunities for error. Furthermore, a well-written suite of tests can serve as a form of living documentation. When you want to understand what a particular part of the system does, you can look at its tests. They illustrate its expected behavior in concrete, executable terms, often more accurately and reliably than outdated written documentation. Emergent design. Letting design evolve organically. Traditional software development often starts with a grand design upfront. Architects spend significant time planning every component, every interface, every interaction. While beneficial for understanding the overall scope, this big design upfront, BDUF, can lead to problems. Assumptions. Designs are based on assumptions that may prove incorrect once coding begins or requirements evolve. Rigidity. It can be very difficult and costly to change a comprehensive upfront design once development is underway. Overengineering. Building for perceived future needs that never materialize. TDD embraces emergent design. Instead of a fixed, detailed blueprint for every single component, design evolves incrementally and organically from the ground up, driven by the needs of the tests. You start with the smallest possible behavior, test it, implement it, and refactor. As you add more tests and more functionality, patterns emerge. Duplication becomes apparent. Opportunities for abstraction arise. The refactoring step, supported by your safety net of tests, allows you to seize these opportunities and shape your design continuously. This doesn't mean there's no planning in TDD. You still need an overall architectural vision. But TDD lets the detailed, granular design emerge iteratively, informed by concrete feedback and actual code, rather than speculative anticipation. This makes the design more robust, adaptable, and relevant to the actual problems being solved. Beyond design patterns, TDD's contribution. You might be familiar with design patterns, established solutions to common software design problems, e.g., factory, singleton, observer. While TDD doesn't replace the need to understand these patterns, it creates an environment where good design naturally emerges, even if you're not explicitly applying a complex pattern. The relentless pressure to make code testable, modular, and concise, coupled with the freedom to refactor, inherently leads developers to write more loosely coupled, cohesive code. This often aligns with the principles that many design patterns embody. You might find yourself implementing a simple version of a pattern without even realizing it, simply because it's the most testable way to structure your code. In essence, TDD trains your design muscles. It provides continuous practice in breaking down problems, isolating concerns, and structuring code for clarity and testability. The tests aren't just guards against bugs. They are silent mentors, gently nudging you toward better design decisions, building the kind of robust, flexible software that can truly withstand the test of time and change. Chapter 5. Beyond bug fixes. The broader benefits of test-driven development. By now, you understand that test-driven development is about much more than just finding bugs. It's a design process, a development rhythm, and a mindset. But what are the tangible, real-world returns on this investment? Beyond the obvious quality improvements, TDD offers a surprising array of benefits that transform not just the code, but the entire development experience. Living documentation. How tests serve as executable specifications. Imagine a world where your software documentation is always up-to-date, accurate, and most importantly, executable. No more stale, forgotten documents that quickly become irrelevant as the code evolves. This is exactly what a well-maintained suite of TDD tests provides: living documentation. Each test case describes a specific behavior of your system. When you read a test like given a user with a valid login when attempting to access a secured page, then the user should be granted access. You immediately understand a piece of the system's functionality. And because these tests are run constantly, ideally after every code change, they are guaranteed to accurately reflect the current behavior of the code. If the code changes and the behavior described by the test is no longer true, the test will fail, alerting you to update either the code or the test itself. For new team members, exploring the test suite can be far more illuminating than wading through complex, static design documents. The tests tell a story of how the system is intended to work, covering both typical scenarios and edge cases. They become the ultimate source of truth, evolving alongside the application itself. The safety net, increased confidence to refactor and make changes. One of the greatest fears in software development is the fear of breaking existing, working code. This fear often leads to a phenomenon known as code rot. Developers become hesitant to touch older, complex sections of code, even when refactoring is sorely needed. The codebase becomes brittle, harder to maintain, and accumulates technical debt. TDD builds an invaluable safety net that liberates developers from this fear. With a comprehensive suite of automated tests, every time you make a change, you can run all tests to ensure that no existing functionality has been inadvertently broken. This confidence allows developers to refactor aggressively, improve the internal structure of the code without worrying about introducing regressions. This keeps the code base clean, readable, and maintainable over time. Embrace change, requirements evolve. With a strong safety net, adapting to new features or changes in existing logic becomes less risky and more manageable. Ship with confidence. When it's time to release a new version of the software, the team can do so with a much higher degree of certainty that the core features are working as expected. This safety net transforms the development process from a precarious tightrope walk into a confident, well-supported journey. Faster development, long-term, countering the slowing down myth. A common misconception about TDD is that it slows down development. On the surface, taking the time to write tests before writing code might seem like an overhead. And in the very short term, for tiny, isolated tasks, this might appear true. However, this perspective misses the forest for the trees. The initial investment in TDD pays dividends many times over due to reduced debugging time. Bugs are caught immediately as they are introduced, often within seconds of writing the code. Compare this to traditional methods where a bug might be discovered days or weeks later, requiring extensive time to track down, reproduce, and fix. The cost of fixing a bug increases exponentially the later it is found. Fewer production incidents. High-quality code with fewer defects means fewer critical issues in live production environments, which avoids costly downtime, reputational damage, and frantic emergency fixes. Easier onboarding. New developers can quickly understand the system by studying the living documentation provided by the tests, reducing the time it takes for them to become productive. Accelerated feature development. A clean, modular, and well-tested codebase is inherently easier to extend and modify. Adding new features becomes faster because you're building on a solid, reliable foundation, rather than battling existing technical debt. While the first mile might feel a bit slower, the marathon of software development is completed much faster and with greater consistency when TDD is in play. It's an investment in sustainable speed. Enhanced communication. How tests clarify requirements and team understanding. Tests are not just for machines, they are a powerful communication tool for humans. When requirements are articulated as concrete, executable tests, ambiguity evaporates. For developers, tests provide clear, unambiguous definitions of what done means for a particular piece of functionality. For team leads and product owners, tests can be shared with non-technical stakeholders to illustrate desired behaviors. A product owner might not understand a code snippet, but they can understand a test scenario. This fosters a shared understanding and reduces misunderstandings. For testers, QA. While TDD significantly shifts the role of manual testing, it doesn't eliminate it. Manual testers can use the automated tests as a guide, knowing what is already covered, and focus their efforts on broader end-to-end scenarios, user experience, and exploratory testing. In essence, tests provide a common language that transcends traditional departmental boundaries, leading to a more cohesive and efficient development process. Reducing technical debt proactively. Building quality in. Instead of treating quality as an afterthought, TDD integrates it into the very fabric of the development process. By forcing developers to think about testability and design first, TDD encourages a proactive stance against technical debt. Prevention over cure. TDD prevents the accumulation of certain types of technical debt, like tightly coupled, untestable code, by making it immediately obvious when such design choices are being made. Continuous refactoring. The constant refactoring step, supported by the test suite, ensures that the codebase remains clean, readable, and maintainable. This means technical debt is addressed and paid down in small, manageable increments, rather than allowing it to pile up into an overwhelming mountain. In conclusion, TDD doesn't just promise robust code. It delivers a transformation in how software is developed. From ensuring living documentation and fostering boundless confidence to accelerating long-term development cycles and reducing technical debt, the benefits extend far beyond simply catching bugs. TDD equips teams with the tools and mindset to build and evolve software in a sustainable, efficient, and enjoyable manner. Chapter 6: Navigating the TDD Terrain. Common Challenges and Misconceptions. Test-driven development offers a compelling vision of software development: confident changes, robust systems, and cleaner designs. However, like any powerful discipline, it comes with its own set of challenges, misconceptions, and a learning curve. Understanding these hurdles beforehand can help you navigate the TDD terrain more effectively and ensure a smoother adoption. It slows us down, addressing the immediate perception versus long-term reality. This is, by far, the most common objection raised against TDD. At first glance, writing tests before writing the functional code seems like an additional step, thus implying more time. A developer new to TDD might genuinely feel slower in their initial attempts. The perception: I could have just written the code directly. Writing tests takes time away from writing features. Our deadlines are too tight for TDD. The reality: the initial feeling of slowdown is often real, particularly for developers learning the TDD rhythm. It requires a shift in thinking, as well as developing new muscle memory for the rapid red-green-refactor cycles. However, this initial friction is quickly offset by significant long-term gains: reduced debugging time. As discussed, catching bugs within seconds of introduction, rather than hours or days later, provides massive time savings. The time you spend writing tests up front is often hours less than the time you would have spent debugging. Fewer production incidents. Stable, well-tested code means less firefighting, less downtime, and less urgent bug fixing once the software is deployed. Increased confidence, faster changes. The safety net of tests allows for rapid, confident refactoring and feature additions. You spend less time worrying if your changes will break something and more time actually building. Better design, less rework. The design benefits of TDD lead to more modular, maintainable code. This means less time spent untangling, spaghetti code, and rebuilding features due to poor initial design. Think of it like building a house. Initial time spent on a solid foundation and detailed blueprints might make the very start of the project seem slower than just piling bricks. But it prevents costly structural failures and rework down the line, ultimately leading to a faster, stronger, and more resilient structure. The learning curve: acknowledging the initial investment. TDD is a skill, and like any skill, it requires practice and patience to master. It's not something you can pick up in an afternoon. Shifting mindset. The biggest challenge is often the cognitive shift from code first to test first. It requires learning to think about behavior and specifications before implementation. Writing good tests. Crafting effective, focused, and maintainable tests is an art form. Overly complex tests, tests that break easily, or tests that don't truly verify behavior can be counterproductive. Discipline and consistency. TDD requires consistent application of the red-green-refactor cycle. Slipping back into old habits can undermine the benefits. Strategy: start small. Pick a low-risk, isolated piece of functionality and commit to using TDD. Don't expect perfection immediately. Embrace the process, learn from your failures, and celebrate your small successes. Many teams find success by pairing up, where experienced TDD practitioners can mentor newcomers. Only for unit tests. Clarifying TDD's focus. Another common misunderstanding is that TDD is exclusively for writing unit tests. While it's true that the red-green-refactor cycle is primarily applied at the unit level, testing the smallest, isolated parts of your code, TDD, is a design methodology that influences your entire system. TDD is primarily for unit-level design. It makes the local code clean, well-factored, and testable. But its benefits extend to integration and system levels. A system composed of well-tested, modular units. The result of TDD is inherently easier to integrate and less prone to integration failures. While TDD generally doesn't involve writing full end-to-end acceptance tests first, A TD2D system is much more stable and reliable at that level. The test pyramid. A common mental model in software testing is the test pyramid, which suggests a large base of fast, fine-grained unit tests, a smaller layer of integration tests, and an even smaller layer of slow, broad end-to-end UI system tests. TDD predominantly focuses on building that solid, wide base of quick unit tests, freeing up other types of testing to focus on their specific concerns. TDD doesn't replace other forms of testing, like integration testing, performance testing, security testing, or manual exploratory testing. It foundationally strengthens the code, making those other tests more effective and often less necessary for basic functional validation. Legacy code woes. Applying TDD principles to existing, untested systems. Trying to introduce TDD into an existing, large, and untested codebase, often called legacy code, can be particularly challenging. You can't just slap a test on top of a giant, tangled function and expect it to work. Such code is often tightly coupled and not designed for testability. The strangler fig pattern. One common strategy is to treat the legacy system like a strangler fig tree. Instead of trying to rewrite the entire legacy system, you gradually build new features and components using TDD, wrapping, or integrating them with the existing system. Over time, the new tested code strangles or replaces the old, untested parts. Characterization tests. Before changing legacy code, you can write characterization tests. These are tests that capture the current observable behavior of the legacy code, even if that behavior is buggy or suboptimal. You then run these tests, make a small change, and ensure the tests still pass. This gives you a safety net for gradual refactoring and modification. It's a marathon, not a sprint, when applying TDD to legacy systems. Small, incremental wins build confidence and momentum. Overtesting versus undertesting. Finding the balance. When new to TDD, developers sometimes struggle with the right amount of testing. Overtesting. Writing tests for every trivial getter-setter, or tests that are overly rigid and break with minor refactorings, known as fragile tests. This can lead to test suites that are slow, bulky, and difficult to maintain. Undertesting. Not testing key behaviors or testing at too high a level, leaving gaps in coverage and compromising the safety net. Tests become mere smoke tests instead of detailed specifications. Strategy. Aim for tests that are specific. Test one small behavior at a time. Readable, clear about what they are testing. Fast, they should run in milliseconds to support the rapid feedback loop. Independent, each test should be able to run in isolation without relying on the order of other tests or global state. Robust, should only fail when the behavior changes, not when internal implementation details change. The balance comes with practice and experience. Think of what you are trying to specify with the test, rather than just what you are trying to check. The test smells, recognizing indicators of poorly written tests. Just as code smells indicate problems in your functional code, test smells indicate problems in your test suite. Fragile tests. Break frequently for reasons unrelated to actual functional changes, e.g., dependent on order of execution, or too tied to implementation details. Giant tests. Try to test too many things at once, making them hard to understand and debug when they fail. Slow tests take too long to run, discouraging developers from running them frequently. Untrustworthy tests. Tests that sometimes pass, sometimes fail, flaky tests, eroding confidence in the test suite. Tests that duplicate logic. Replicate the same logical conditions as the code under test, meaning they might pass even if the logic is buggy. Recognizing these smells is the first step to improving your test suite, ensuring it remains a valuable asset rather than a liability. Navigating the TDD terrain involves acknowledging these challenges, but also understanding the strategies to overcome them. The benefits of TDD, as we've explored, far outweigh these initial hurdles, offering a path to more confident, productive, and ultimately, more fulfilling software development. Chapter 7, TDD in Action. A story of building with tests, conceptual case study. Up to this point, we've discussed the philosophy, the mechanics, and the profound benefits of test-driven development. We've acknowledged that it's a design process, a safety net, and a driver for superior software. But how does it feel? What does the red-green-refactor cycle look like when you're actually building something, step by step, with tests guiding your way? Since this book avoids specific programming code to remain accessible, we'll embark on a conceptual journey. Imagine we're a software development team tasked with building a small but useful piece of functionality. A text analyzer. Its initial requirement is modest. It needs to be able to tell us the number of words in a given piece of text. Let's watch TDD in action, not through lines of code, but through the thought process and iterative steps that lead to a robust solution. Setting the stage, the initial requirement. Our product owner, or our own internal thought process, has given us a clear directive. We need a text analyzer that can count words. Traditional approach, without TDD. A developer might immediately start coding, define a function count words, text, then start thinking about how to split the text, handle punctuation, etc. They'd write the whole thing, then maybe test it manually, or by writing a few simple tests afterwards. TDD approach, our story begins, we resist the urge to code immediately. Instead, we pull out our metaphorical test writing toolkit. Step 1, define the simplest failing test. Okay, we think, what's the absolute simplest behavior for counting words? Thought process. The easiest text is probably an empty one. What's the word count of an empty string? 0. Our first test, conceptual, name, should return 0 for empty text. Scenario, given an empty piece of text, e.g., when. The text analyzer is asked to count words. Then, the result should be 0. We write this test. When we attempt to run it, it fails. Why? Because our text analyzer doesn't exist yet, much less a count words function within it. This is exactly what we want. We have a clear, failing signal, confirming our test is valid and that the desired behavior is absent. Our status, red. Step 2, green, make the test pass, minimal implementation. Now, we need to make that test pass, with the absolute minimum amount of code. Thought process, to make should return 0 for empty text pass, our count words function, when given an empty string, must return 0. Our code change, conceptual. We create a text analyzer component. Add a count words function to it. Inside count words, for now, we just return 0. Yes, even if the input isn't empty, it's just enough to pass the current test. We run the test again, it passes. All previous tests, well, just this one, are now green. Our status, green. Step 3, refactor, improve the code, no behavior change. Our current count words function is ridiculously simple. It always returns 0. There's nothing truly complex to refactor yet, but we ask, is the code as clear and simple as it can be? Is it doing more than it should? In this case, return 0 is as simple as it gets. Thought process. No immediate refactoring needed for our return 0 here. We do a quick check, make sure our component, function names, etc. are clear. Our status, green and clean. We are now ready for the next piece of functionality. Step 4, define the next failing test. What's the next logical step after empty text? A single word. Thought process. If the text has one word, the count should be 1. Our second test, conceptual, name, should return 1 for single word text. Scenario, given a piece of text with one word, e.g., hello, when the text analyzer is asked to count words. Then, the result should be 1. We write this test. We run all tests. Our new should return 1 for single word text fails, because our function still just returns 0. Crucially, our first test, should return 0 for empty text, still passes. This is our signal. The new test provides a clear requirement, and the old one ensures we haven't broken existing functionality. Status, red. Step 5, green, make the test pass, minimal implementation. Now, we need to make the new test pass without breaking the old one. Thought process, we need actual word counting logic. The simplest way is to check if the input text is empty. If it is, return 0. Otherwise, count 1 for now. Our code change, conceptual, inside count words function. If text is empty, return 0. Else for now, return 1. We run all tests. Both should return 0 for empty text and should return 1 for single word text pass. Status, green, step 6. Refactor, improve the code. Again, our code is pretty minimal. Still, is there any duplication? Any way to make it clearer? Not really. Thought process, no obvious refactoring needed yet. The logic handles our two simple cases. Status. Green, step 7. Red, define a more complex failing test. Time for multiple words. Thought process, 2 words. What about spaces? Our third test, conceptual. Name, should count multiple words separated by space. Scenario, given. Text with multiple words, e.g., hello world, when the text analyzer is asked to count words. Then, the result should be 2. We write this test. Run all tests. Should count multiple words separated by space fails, because our count words function still returns 1 for any non-empty string. Our previous tests still pass. Status, red, step 8. Green, make the test pass, evolving implementation. This is where our count words function truly starts to take shape. Thought process, we need to split the text by spaces. Our code change, conceptual, inside count words function. If text is empty, return 0. Else, split text by space, count the resulting part's words, and return that count. We run all tests. All 3 tests pass. Status, green, step 9. Refactor, improve the code. Now we have some actual logic. Let's look for opportunities. Thought process. The if text is empty check could be folded into the general logic of splitting and counting. If we split an empty string, we usually get an empty list of parts whose count is 0. This simplifies the code. Our code change, conceptual, inside count words function, revised. Split text by space, count the resulting parts, words, and return that count. The empty string case is now naturally handled. We run all tests after refactoring. All tests still pass. This is the safety net in action. We made an internal structural change, but the observable behavior tested by our comprehensive suite remained identical. Status, green, the ongoing story. We would continue this cycle, red. Add a test for text with leading trailing spaces, e.g., hello world should still be 2. Green, adjust split logic to trim spaces. Refactor, simplify, red. Add a test for multiple spaces between words, e.g., hello world should still be 2. Green, adjust split logic to handle multiple delimiters. Refactor, refine, red. Add a test for punctuation, e.g., hello world should be 2. Green, adjust logic to remove punctuation before counting. Refactor, perhaps extract a clean text helper function because it's growing. Red, add a test for non-word characters, e.g., hello 123 world should be 1, or perhaps 2, depending on definition. TDD helps clarify this. Each small step guides our development. Our text analyzer component gets smarter, but it does so through a series of tiny, validated improvements. At any point, our entire test suite confirms that everything we've built so far still works. This iterative, test-driven approach helps clarify requirements, ensures quality, and builds confidence in the emerging design, allowing the text analyzer to grow robustly and confidently. Chapter 8, TDD and the Team, Integrating into Agile and Modern Workflows. Test-driven development, while seemingly a lonely pursuit performed by a single developer at their keyboard, is in fact a highly social and collaborative practice. It thrives in environments that value rapid feedback, continuous improvement, and shared understanding. This makes TDD an exceptional fit for modern software development methodologies, particularly Agile frameworks, and a cornerstone for smooth continuous integration and delivery pipelines. TDD as an Agile practice. Agile methodologies, such as Scrum, Kanban, and especially extreme programming XP, prioritize working software, collaboration, and responsiveness to change. TDD aligns perfectly with these values. Working software over comprehensive documentation, TDD's living documentation. The test suite provides an always up-to-date, executable specification of behavior. This is far more valuable than static, outdated documents frequently found in traditional, waterfall approaches. Teams can trust the tests to reflect what the software actually does. Individuals and interactions over processes and tools. TDD fosters a culture of shared responsibility for quality. Developers are empowered to own the quality of their code from the outset. Customer collaboration over contract negotiation. While customers rarely write tests directly, the clarity of thought required for TDD helps developers better understand and interpret customer requirements, leading to clearer conversations and fewer misunderstandings. Each test written represents a tiny, concrete piece of a customer's desired outcome, responding to change over following a plan. The robust safety net provided by comprehensive test suites means teams can adapt to new requirements or changes in priorities with significantly less risk. Refactoring code to accommodate new features becomes a routine activity, not a dreaded one. Extreme programming, XP, TDD originated as a core practice within XP, alongside other complementary practices like pair programming, two developers working at one computer. One writes the test, red phase, the other writes the code to make it pass, green phase, and then they collaborate on the refactor step. This fosters knowledge sharing, immediate code review, and adherence to TDD discipline. Collective code ownership. Everyone on the team is responsible for the quality of all code. TDD facilitates this by making the code easier to understand via tests as documentation and safer to change via the safety net. Simple design. TDD naturally promotes simple, minimal, and clear designs which are easier to maintain and extend. In an agile context, TDD is not just a tool, it's an enabler for the very principles that make agile effective. Collaboration through tests, a common language. Tests are incredibly powerful communication tools within a team, and even with non-technical stakeholders. Developers talking to developers. When a new developer joins a team, they can quickly understand the behavior of existing code by reading its tests. They don't need a lengthy handover or complex architectural diagrams for every detail. The tests clearly delineate what each component is supposed to do. Developers talking to quality assurance, QA, TDD changes the relationship between developers and QA. Instead of QA being the sole bug finder at the end of the cycle, they become partners in quality. QA can review tests to ensure requirements are fully captured, and then focus their efforts on higher-level testing, e.g., user experience, end-to-end flows, performance, security, rather than merely basic functional validation. The automated tests free up QA to do more meaningful work. Tests as specification checkpoints. For teams practicing behavior-driven development, BDD, which builds upon TDD, tests are often written in a language close to natural human language, e.g., gherkins given when then syntax. This allows product owners or business analysts to directly review and validate the executable specifications, ensuring shared understanding of what needs to be built. While pure TDD tests are often more code-centric, their clear naming and focus on a single behavior still convey intent effectively. This shared understanding, facilitated by tests, reduces miscommunication, speeds up decision-making, and fosters a more collaborative environment where everyone is working towards the same, clearly defined goal. Continuous integration and delivery, TDD's foundation. Modern software development heavily relies on continuous integration, CI, and continuous delivery deployment, CD. Continuous integration, CI. Developers frequently integrate their code changes into a shared mainline. For CI to be effective, every integration must be validated quickly. This is where TDD's automated tests are absolutely non-negotiable. After a developer commits their code, an automated CI server immediately runs the entire test suite. If any test fails, the build is broken, and the team is instantly alerted. This prevents defects from accumulating and ensures the codebase is always in a deployable state. Without fast, reliable automated tests, like those produced by TDD, CI becomes a slow, painful, and ineffective bottleneck. Continuous delivery deployment, CD. Once the build is verified by CI, it can then be automatically deployed to various environments, staging, production. CD relies entirely on confidence in the automated testing. If your test suite is comprehensive and reliable, as a TDD-generated suite typically is, then you can have high confidence in automatically deploying changes with minimal human intervention. TDD provides the bedrock of quality assurance that makes CD feasible and safe. In essence, TDD acts as the quality gate for CI/CD. It ensures that the very foundation of your software is solid, enabling the efficiency and speed gains promised by these modern DevOps practices. Cultivating a TDD culture. Strategies for adoption. Adopting TDD within a team or organization isn't just about learning the Red-Green-Refactor cycle. It's about cultivating a culture that values engineering discipline, proactivity, and continuous learning. Lead by example. The most effective way to introduce TDD is for team leads or experienced developers to consistently practice it themselves and demonstrate its benefits. Start small. Don't try to mandate TDD for every single task on day one, especially in a legacy codebase. Choose new, isolated features or components. Provide training and mentorship. Offer workshops, bring in experts, and pair experienced TDD practitioners with newcomers. Emphasize the why. Continuously articulate the benefits of TDD beyond just testing. Focus on design, confidence, and long-term speed. Dedicated refactoring time. Build a culture where refactoring is seen as an essential part of development, not an optional extra. The green refactor phase needs to be respected. Celebrate successes. Highlight improvements in code quality, reduction in bugs, and faster delivery cycles attributable to TDD. Be patient. TDD is a skill that takes time to internalize. Some developers will grasp it faster than others. Support and encouragement are key. Integrating TDD into a team's workflow fosters a shared sense of ownership, provides clarity, and builds a robust foundation for rapid, reliable software delivery. It helps teams not just build software, but build better software together. Chapter 9, Mastering the Craft, Advanced TDD Concepts and Best Practices. As you become comfortable with the fundamental Red-Green Refactor cycle, you'll inevitably encounter situations that challenge your understanding. This chapter delves into some slightly more nuanced, though still conceptually explained, aspects of TDD, helping you refine your craft and tackle more complex testing scenarios. We'll explore how to handle dependencies, the subtle differences between test types, and some best practices for writing truly effective tests. Beyond the basics, isolating components with test doubles. In our conceptual text analyzer example, we dealt with a self-contained component. But what happens when your code needs to interact with external systems, like a database, a web service, or even another complex part of your application? These interactions are called dependencies. Running a unit test that connects to an actual database server or calls a live API endpoint would violate many of our TDD principles. Speed. Real database calls are slow, breaking the fast feedback loop. Isolation. The test might fail not because of an issue in your code, but because the database is down or the network is slow. They also make it difficult to test specific failure scenarios. Reproducibility. Test outcomes might vary depending on the state of the external system. This is where test doubles come into play. A test double is a generic term for an object that stands in for a real object or dependency during testing. Think of them like stunt doubles in a movie. They look and behave enough like the real thing for the purposes of the scene, but they are entirely under your control. Common types of test doubles, explained conceptually. Stubs. Provide canned answers to method calls made during the test. Your code asks the stub for some data, and the stub responds with pre-configured data. You set up a stub to return specific values so your code can proceed as if it was talking to the real dependency. Analogy, calling a movie ticket hotline and a recording tells you seats are available. It's not a real person, but it gives you the specific information you need for your next decision. Mocks. Not only provide canned answers, but also verify that certain methods were called on them, and with specific arguments. Mocks are used to test interactions and ensure your code is calling its collaborators correctly. Analogy. You call a sophisticated customer service bot, and it not only answers your question, but also logs that you called, what you asked, and what time. Later, you check the logs to see if that interaction occurred as expected. The act of using test doubles forces you to design your code so that dependencies can be easily swapped out. This is a key driver for loose coupling and dependency injection techniques, which are hallmarks of good, testable design. TDD doesn't just encourage this, it practically demands it, making test doubles an essential tool in your TDD toolkit for testing isolated units. The role of integration tests. Beyond the unit. While TDD primarily focuses on unit tests, small, fast, isolated tests of individual components. These don't exist in a vacuum. A system is made of many units working together. This is where integration tests come in. Unit tests, TDDs, focus. Verify that individual components work correctly in isolation. They are fast, reliable, and provide immediate design feedback. Integration tests. Verify that different components or services work correctly together. This might involve testing how your code interacts with a real database, a file system, or an external API. You wouldn't typically use the Red-Green-Refactor cycle for integration tests in the same way you do for unit tests. Why? Because integration tests are slower and involve external factors, meaning their failures are less precise signals for immediate design changes. Instead, the TDD process builds a strong foundation of unit-tested components. Then, integration tests act as a verification layer on top, ensuring that these well-tested units can successfully communicate and cooperate. The test pyramid, mentioned in Chapter 6, wisely suggests having many fast unit tests, fewer integration tests, and even fewer slow end-to-end user interface tests. TDD helps you build that wide, solid base efficiently. Thinking testable, writing code with testability in mind. TDD naturally pushes you towards writing testable code. But what exactly makes code testable? Predictable input, predictable output, pure functions. Functions that, given the same inputs, always produce the same outputs and have no side effects. Like modifying global state or interacting directly with external systems, are incredibly easy to test. Clear responsibilities. Classes or functions that have a single, well-defined purpose are much easier to test in isolation. Manageable dependencies. Code that doesn't directly create its dependencies, but instead receives them, e.g., through constructor injection, is easier to test with doubles. Avoidance of global state and singletons. These can make tests interdependent and unpredictable. Thinking testable means constantly asking, how would I verify this behavior in an isolated test? If the answer feels complex, your design might be telling you something. Test naming, the art of clarity. A test's name is its most important piece of documentation. A good test name should immediately convey what it's testing and what the expected outcome is. Consider these approaches, given when then. Describes the setup, the action, and the expected result. Example, give an empty text when counting words then return 0. Should describes a direct behavior. Example, count words should return 0 for empty text. Avoid generic names like test1, my test, or test word count. A well-named test tells a story. If a test name is long or difficult to phrase, it might be a test smell, indicating that the test is trying to verify too much, or the unit under test has too many responsibilities. Behavior-driven development, BDD, an evolution from TDD. While TDD focuses on how developers implement functionality, behavior-driven development, BDD, focuses on what the system should do from the perspective of its users, collaborating stakeholders, and developers. BDD evolved from TDD and shares many of its principles. BDD features focus on behavior. Instead of just tests, BDD emphasizes specifying behaviors. Shared language. BDD uses a common, ubiquitous language, often expressed in a given when-then format, like our test names, that is understandable by technical and non-technical team members alike. Emphasis on examples. Behaviors are illustrated with concrete examples. BDD typically starts at a higher level than TDD, e.g., specifying an entire user story's behavior, and then drives down to the unit-level TDD practices. Tools like Cucumber or SpecFlow help translate these human-readable specifications into executable tests. The point is not just to test the code, but to derive a shared understanding of what needs to be built. Mastering TDD is a continuous journey. By understanding test doubles, recognizing the roles of different test types, and practicing good test naming conventions, you can elevate your TDD practice, ensuring your tests remain valuable assets that confidently guide you toward crafting clean, robust, and adaptable software. This deeper understanding will empower you to tackle increasingly complex software challenges with the same confidence and discipline cultivated throughout your Red-Green-Refactor cycles. Chapter 10. Your TDD Journey. the path forward, and continuous improvement. You've embarked on a journey through the principles of test-driven development. We've demystified its core cycle, delved into its profound design benefits, highlighted its broader impact on quality and productivity, navigated common challenges, and gotten a conceptual feel for how it works in practice. Now, as you reach the end of this book, the real journey begins, applying TDD in your own work and continuing to grow as a software craftsman. Starting small, thinking big. Practical advice for adoption. The prospect of entirely changing your development habits can feel daunting. Here's some practical advice for adopting TDD, whether you're an individual developer or part of a team. Start with new code. It's easiest to begin TDD on greenfield projects or new modules within an existing system. Retrofitting TDD onto complex, untested legacy code is a much harder task, though not impossible, as discussed in Chapter 6. Begin where the path is clearest. Focus on small, isolated units first. Don't try to build an entire end-to-end user interface with TDD on day one. Pick a small, self-contained piece of logic, like a data validation rule, a calculation, or a text parsing function, just like our text analyzer example. These small victories build confidence. Embrace the red-green-refactor rhythm zealously. For a while, be dogmatic about the cycle. Don't skip the red phase, and don't make code pass without seeing the test fail first. Don't skip the refactor phase. Over time, this discipline will become muscle memory. Pair program if possible. If you're on a team, find a willing colleague and try pair programming with TDD. One person drives at the keyboard, while the other navigates, guides the process, thinks about the next test. This provides immediate feedback, transfers knowledge, and helps reinforce the discipline. Use your tools, leverage your IDE's test running capabilities. Make running all tests a near constant habit. Fast feedback is crucial. Seek feedback and mentorship. If you know someone experienced with TDD, ask them to review your tests or even pair with you. Learning from others is invaluable. Don't strive for 100% coverage immediately. While a high degree of test coverage is a natural outcome of TDD, it shouldn't be the primary goal. Focus on testing behavior and driving design. As you get better, coverage will naturally increase. Remember, TDD is a skill. You wouldn't expect to play a musical instrument perfectly after reading a book, nor should you expect to master TDD overnight. Consistent practice, patience, and persistence are your greatest allies. Perseverance and patience, the long game of mastery. There will be moments of frustration. Your tests might not be as clear as you want, or you might struggle to isolate a dependency. You might inadvertently skip the red phase and catch a test passing that you expected to fail. This is all part of the learning process. Revisit the why. When you feel stuck or frustrated, remind yourself of the significant long-term benefits. Fewer bugs, cleaner designs, increased confidence, and a more enjoyable development process. Acknowledge the investment. The initial time investment in learning and adopting TDD is real. But compare it to the hidden costs of not doing TDD: endless debugging, brittle code, project delays, and developer burnout. The payoff is worth it. It's a marathon, not a sprint. Don't aim for perfection, aim for progress. Each successful red-green-refactor cycle, no matter how small, is a step forward. Continuous learning, the evolving landscape. The world of software development is constantly evolving. While the core principles of TDD remain timeless, new tools, frameworks, and related practices emerge regularly. Deepen your knowledge. Consider reading Kent Beck's Test-Driven Development by Example, which provides concrete code examples and insights from the originator. Explore books or articles on clean code, refactoring, and software design patterns. These concepts are highly complementary to TDD. Explore related practices. Look into behavior-driven development, BDD, which bridges the gap between technical tests and business requirements. Understand how TDD fits into broader DevOps practices and CI/CD pipelines. Stay curious, follow thought leaders, attend workshops or conferences, and engage with online communities. Share your experiences and learn from others. Your TDD journey doesn't end with this book. It merely helps you take your first deliberate steps. TDD in the wild, its enduring relevance. TDD has been around for over 2 decades, and its principles remain as relevant as ever. In a software landscape demanding ever-increasing speed, quality, and adaptability, TDD provides a robust and reliable way to meet these challenges. From small startups to large enterprises, successful teams around the globe leverage TDD to build resilient, maintainable, and high-performing software systems. It's not just a trend, it's a proven engineering discipline that enables continuous improvement in software craftsmanship. Final call to action: embrace the transformation. The hidden costs of crafting code without TDD. The bugs, the technical debt, the fear of change, the slow, painful releases are all too real. You now have a powerful alternative. Test-driven development is more than a technique. It's a commitment to building quality in from the very beginning. It's a way to reclaim joy in your development process, transforming challenges into opportunities for growth and mastery. It provides a unique blend of discipline and creativity, enabling you to design elegant solutions one small, verified step at a time. Your code is your legacy. Make it robust, make it maintainable, and make it with confidence. Embrace the Red-Green-Refactor rhythm. Embrace the feedback. Embrace the transformation. Your journey with test-driven development starts now. Build better software, faster, and with confidence.